Hello to everyone. Welcome to another seminar of the Astronomy Department of the IAG-USP, and thank you for your presence. Today we have the honor of having the presence of Professor Marcelle Soares-Santos from University of Michigan in the US. Professor Marcelle, thank you for accepting this invitation, for being here today. I'll tell a little bit about Marcelle. For those who do not know her, she got her bachelor in physics at the Universidade Federal do Espírito Santo in 2004. Marcel then got her master and PhD degrees in astrophysics here at IAG-USP, and she defended her thesis in 2010, right, Marcel? Since then, after this, she worked as an associate scientist at the Fermi National Accelerator Laboratory, and later on as assistant professor of physics at Brandeis University in US. And currently, Professor Marcel is a faculty member of the University of Michigan in the Department of Physics. Her focus is on the investigation of the nature of the accelerated expansion of the universe, and her team detected the first neutron star collision ever observed, I think in 2017. And some of her awards I will mention here is the Precision Sloan Research Fellowship in 2019 and the Cottrell Scholar Awards in 2021. And today, Marcel is going to present the seminar Cosmology in the Era of Multi-Messenger Astronomy with Gravitational Waves. Questions can be asked to Marcel after her presentation. If you are following the seminar in the YouTube channel, you can write your questions in the chat. I will bring it to Marcel after the presentation. And before the seminar starts, I would like to ask everyone to please turn off your cameras and microphones. And Marcelle, feel free to start whenever you want.
Thank you. It is a pleasure to be here. Thank you for this invitation. It is always a pleasure to talk about my research, but in particular, it is great to be able to present a seminar at my home institution. So IAG-USP will always be my home. So I think that this is a really exciting time for me. So let me begin sharing the screen here to get started with the topic of today's presentation. So what I'm going to talk about today is a bit of an overview that includes the story of the discovery of the neutron-star merger known as GW170817. And what you're seeing here in front of you today is a comparison image showing highlighted here on this spot the point in the sky where that merger occurred in August of 2017. And on the other side here, you're seeing the same region 2 weeks later. And so you can have already an idea of one of the challenges involved in this research, which is the time domain observations that we have to observe quickly and efficiently in order to be able to discover the location in the sky where the merger occurred. But this will become more clear as we progress in the seminar today. This talk will include the story of the discovery of this spectacular event that occurred in 2017, but it will also tell you a little bit about what have we been doing, what are we up to since then, right? We are here in 2021. We are preparing to make new discoveries like this. And in particular, in the case of my research group, we are preparing to make precision cosmology measurements with a sample of these events. So it's an exciting time and an exciting research program that I want to share with you here today. So without further ado, let's start with the motivation. This cartoon here illustrates the history of our universe from the early days, you know, at the beginning, at the Big Bang time, all the way to the present. And as the universe expands, what happens is that we have different phases of this expansion. And in different phases, we are going to have different components of the universe dominating the expansion. In particular, we are interested in the recent universe when the rate of expansion is accelerating, and we don't really know what is the physics of the component that drives this acceleration. And this is exciting because we are, as physicists, we are in the business of trying to understand what is governing, you know, what are the laws governing the nature of what we observe in all scales. And we have here something that is happening at the largest possible scale, and we really have no idea of what is the underlying physics. So it is really exciting to try to understand what is the physics of the accelerating universe, expanding universe, in what is dark energy. One of the ways that we can do this observationally is to look into the distance redshift relation. And the idea here is that we know that photons traveling from, say, a galaxy far, far away, and are being detected here on a telescope on Earth, the wavelength will be stretched out so that the photon will look redder than it was at the point of emission. And the reddening, the redshift, is going to be proportional to how much the expansion occurred from the point of emission to the point you see it here. So making measurements of distance and redshift for objects at different points in the cosmic history is really important because it allows us to map out the history of cosmic expansion. This method, or this idea, has been explored for a long time. It was throughout the 20th century. We made great improvements in our ability to measure distances to objects. In particular, the type 1a supernova are a key type of astronomical event for us to explore. What you're seeing here in this plot is the result that was obtained by two different groups who observed supernova at various redshifts, and obtained here their distances, showing that not only showing what was the rate of expansion of the universe today, but showing that this rate of expansion is not constant. This rate of expansion is increasing. So these two groups discovered the accelerated cosmic expansion using these supernova observations, and they were awarded the Nobel Prize in 2011 for their discovery. This discovery revolutionized our field in the sense that we now know that more than 2/3 of the universe today is made of dark energy, and yet we have no idea of what is the underlying physics. We don't know if this is a new fundamental force, or if it is gravity behaving in a way that is beyond the scope of the traditional Einstein theory of general relativity. We don't know if we can describe the physics of dark energy using the same theoretical framework of particles and fields that works so well for quantum mechanics and elementary particles. And we also don't know if dark energy is a constant or if it is evolving with time, with cosmic history. So as you can see, there are lots of questions, and oftentimes when I present this problem in lectures like this, I often get, especially from younger audiences, I get questions like, okay, isn't this, too many questions for, too few data points there in the graph? And how, yes? Sorry, I am not sure if there was a question there or not. Okay.
Yeah, probably some noise.
So what I tend to say when people ask me about, the size of the challenge of studying dark energy, I often say that for me, I see this as an opportunity, because if you are in physics and if your motivation is to understand what is happening with the universe and to understand big questions, dark energy is a topic that presents you with many of those questions, and it's a very exciting topic to work on. Now, what I showed here is a plot that is old, right? It is decades old. What has the community accomplished since then in the understanding of dark energy? We have made great improvements in our ability to measure the rate of expansion today. And this plot here summarizes the current status of the field. On the x-axis here, you have the rate of expansion of the universe today, the parameter called h naught. And the data points here corresponds to measurements made with different observables, different techniques. In particular, I call your attention to these 3 red points here. They correspond to measurements made using type 1a supernova. And also this point here, the black point, are measurements made using observations of the cosmic microwave background. So this is radiation from the very early universe. And what you can see here, first, the good news is that the error bars here are tiny. They are of 2.5 and 1%. This is a great achievement. The ability to make measurements with this level of precision is a great achievement of our community. Now, the not so good news is that the measurements with the smallest error bars, they disagree with each other significantly. These error bars, they don't overlap with each other at all. This disagreement is at a level of greater than 5 sigma today, meaning that this is a serious issue that could be from systematic errors in the measurements, but it could also mean new physics. And by new physics, I mean that it could be the clue to what is happening microscopically, because these measurements are made using information coming from the early universe, and these measurements are made using information that is coming from the current universe. So understanding and disentangling this tension between early universe and late universe measurements can provide the clue to understand what dark energy might be. One example of how we could reconcile these 2 discrepant measurements is shown up here in these arrows. So this is showing by how much you would change the result from the Planck 15 result shown here, if we were to change, specific parameters in a cosmological model. In particular, for example, if you were to change the equation of state of dark energy by about 10%, we would already make improvement and make it substantial agreement. So these are only examples of how we could investigate this. What we want to really, in order to make progress and actually answer the question of what is causing this and what is the origin of this tension, what we really need is better data. We need more measurements to put in this plot here, and we need these measurements to be with high precision, so small error bars, and we need them to be independent from these other measurements so that we can compare and make an assessment. Now, new independent measurements are hard to come by, and this is a place where the gravitational waves are coming to our rescue here. And I'm going to explain a bit how that comes about. Before I go into the gravitational wave arena, let me introduce the project that I've been working on for over a decade right now, since the times of my PhD. The Dark Energy Survey is a large-scale imaging survey that covers thousands of square degrees, a substantial fraction of the entire sky, observing supernova galaxies, hundreds of millions of galaxies, in fact, and with the intent of mapping out the history of expansion of the universe and improving our understanding of dark energy. That's why it's called the Dark Energy Survey. In order to pursue these observational programs, the Dark Energy Survey collaboration built the Dark Energy Camera. And what you're seeing here is a picture of the focal plane of this camera with 62 very sensitive CCDs that are very sensitive to light and produce superb high precision images. These high resolution images. This camera has 570 megapixels. It's installed on a 4-meter telescope in Chile. The installation happened in 2012, and I had the pleasure to be part of the team that worked on the construction and commissioning of this camera. We have obtained 6 campaigns of observations with this camera since between 2012 and 2019. And over this time, we accumulated a vast amount of data that we're using to produce, the various analysis that we're doing. Now, something new happened between 2012 and now, and that is the fact that our colleagues in the gravitational wave community have built detectors that are sensitive enough to tiny ripples in space-time when binary systems merge. These gravitational waves that are detected by LIGO and Virgo, they are also accompany. They also come with traditional radiation that we can detect with our camera. So we began in 2015 a program that is called the DESGW program, where we try to find the optical counterpart of LIGO Virgo events. And what I mean by that is that we try to find the bright spot where the merger happened, which you have seen in the first page of this slide. That image highlighting the spot where the merger had happened. That is the goal of the DESGW program, okay? And I am the person that led the beginning of this program, and this is something where we had 3 campaigns of observations together with LIGO, trying to make this program happen. And today I'm going to talk about what's going on.
Excuse me, Marcel. Sorry, interrupting you. Are you showing the slide number 6?
Yes, I should be going
okay.
to. Yes, thank you.
Okay.
Thank you so much. So here is an overview of the first results from DES. And there were many papers published with DES results. I'm showing here only one of them with a combination of parameters omega m, which is the fractional contribution of matter to the total content of the universe today. Remember, I said about 70% is dark energy, so approximately 30% is everything else. And here is amount of clustering in those galaxies. So there's no gravitational waves involved in this plot here, but it is to show, it is meant to show that the DES results are in tension, slight tension with the cosmic microwave background results from Planck here. This tension is not as significant as what I showed before with the supernova, where the separation between the regions covered is really big. But it's another example of this type of tension that we want to explore. And here I am also highlighting that if you're interested in seeing more results from DES, this link here provides a number of results. Now let's go into how those gravitational wave observations can contribute to this program, right? I'd like to show this paper from the 1980s. I'm not expecting people to read through this in detail, but I really like to show this because it was one of the first papers that proposed the idea that we are exploring now, more than 30 years later, right? The idea here being that if there is a binary system, so two neutron stars coalescing, we can compute the rate of change. We can use the rate of change in frequency as the orbits decay to obtain this combination here of the total masses of the system, and the amplitude of the waves is going to be dependent on the same combination of masses here. So what this means is that by measuring in my detector the rate of, say, the LIGO detector, if I measure the rate of change in frequency of the gravitational wave signal, I obtain a prediction for what is the intrinsic amplitude of the waves. So now I can compare with the amplitude of the waves in my detector. I take the ratio of the two, and voila, I have the distance to that event. So this idea is simple, it is clean, and it's also very hard to execute because it requires that we have very sensitive gravitational wave detectors. And for this reason, this idea was not fully implemented until 2015, 2017. So in 2015, the LIGO collaboration came out to the astronomical community saying, we are getting ready to make a detection. If astronomers are interested in pursuing a gravitational wave multi-messenger program, looking for the electromagnetic counterparts, please join us. It's time to get ready. And so our team was one of many teams that responded to that call. And early on, when we started doing this, I started collaborating with colleagues, and two of them made this plot, which I'm showing here today. This is showing the percent confidence level in the area in the sky, right, as a function of that area in square degrees for a number of simulated events. I would say that at the time we were talking about running with only 2 gravitational wave detectors or 3. Okay, these days we have a scenario with 3 detectors operating routinely. But what you can see here is that in the case of 3 detectors, which is much better already than only 2, you need tens, maybe even 150 square degrees in order to have a high confidence that you have the event in that area in the sky. Summarizing here, if you want to reach 90% confidence, you need to cover an area of approximately 55 square degrees in average. This area is large. There are not very many instruments currently that can cover such a large area with the depth that you need to find a source that is very faint. But the dark energy camera in particular is really well suited to this challenge because the field of view of DECam is 3 square degrees, so you can cover this 55 square degrees with less than 20 pointings, and it's on a 4-meter telescope, so we can go deep very quickly. So when I looked at this plot, that was the moment when I was convinced that the program of the DESGW idea was feasible. And I think that was a turning point for us because it motivated our colleagues to jump at the opportunity to make it happen. So here is what we did. Once we realized that we could do it, we decided to step and repurpose an existing piece of software that we had that is responsible for the image processing from images from DECam, and we built this pipeline that I'm showing here. How does this work? Well, when a merger of 2 neutron stars occurs somewhere in a galaxy far, far away, our colleagues in LIGO receive that signal, and they will determine the distance, and they will issue a trigger. This trigger is a signal that comes to us, and our software, we have a piece of software called the main injector, which will receive this trigger, and it will compute what is the optimal plan of observations in the sky to cover, 90% or more of the probability region so that we can find the counterpart. We sent this plan to our colleagues on the telescope and obtain the images, run through the image processing pipeline, and produce a list of candidate objects that later we post-process until we identify the actual counterpart and publish. Here is a plot showing the typical processing times. We want to do this fast, within an hour or so, from the time that you do the observation, because we want to detect the source before it fades away so that it can go back and take more images or take spectra and so on, right? So we did that, and many people worked on the development and implementation of the software pipeline, and this paper here gives you more details. Now let's see this pipeline in action. On August 17, 2017, LIGO received the signal of the first binary neutron star event. Before that, binary black hole events had already occurred, but those events did not have any a counterpart. This one was special because for neutron stars, we had an expectation for the electromagnetic signature to be bright. So we were really excited to see this event. I should say that in this field, the nomenclature is simple: GW for gravitational waves and the date when the event occurs. So every time you see this type of naming convention here, you know that we are talking about this type of event. As I mentioned before, many other teams responded to the initial call from the LIGO collaboration. So at the end, there were over 50 teams, hundreds of institutions involved, and at the end, dozens of papers were published with the results of that observing campaign. It was spectacular to be a part of that. And here, of course, I don't expect people to be reading the names of every team that worked on that, but it's just to give an idea of how much of a collective effort this was. As I mentioned earlier, the neutron star mergers, they are particularly exciting for us relative to the black hole mergers, because we expect to have bright emission coming from these events, and that for an astronomer is gold, right? So what I'm showing here is an illustration of what are the main mechanisms that we expect. On the left side, you see relativistic outflows. The idea here would be particles that are accelerated because there are strong magnetic fields in this system. So this emission is non-thermal, it is beamed, and it is bright in gamma ray, X-ray, and radio wavelengths. This is awesome, it's fascinating, but it's not interesting particularly to me because my camera cannot see in any of these wavelengths. Our camera can see well in optical infrared wavelengths. And so for us, what is important are the subrelativistic outflows. And this is coming from radiation that is emitted from nuclear reactions that happen once the neutron star material gets disrupted. Very close to the merger time, lots of neutron star material gets disrupted, and that disruption causes the neutrons to rapid neutron capture to occur, and this process generates heat, and this heated object is going to be very bright in the sky. We have approximately 1% of a solar mass being ejected, and this material is accelerated to 10 to 30% of the speed of light. Okay, this emission is isotropic, it's thermal, and it's bright in the wavelengths that are good for us to observe. So this is the typical signature that we are looking for. On that day, the first telescopes to see the counterpart of GW170817 were Fermi and Integral, two gamma ray satellites. So this signature here was the first one that was seen. And what you're seeing here is a plot showing the event rates in those satellites. And you can see that the peak is 2 seconds after the merger that was detected by LIGO. So if the story of GW170817 had ended here, it would already have been spectacular. This was the first time ever that multi-messenger observation of a gravitational wave event was done. And by multi-messenger here, of course, I mean gravitational waves and traditional photons from the same event. But I would not be as happy about that because, as I said, we don't work on these wavelengths. But GW170817 was special for many, many reasons. One of them being that there was emission in both channels, right? And so it was important for us as well. So where is this source localized in the sky? Here I'm showing the region, localization region produced by LIGO and Virgo. And this is a zoom in on this highlighted area here. This area in total has approximately 30 square degrees. So it is even better than the average that we had expected back when we were doing simulations in 2015. And what you're seeing here, the little dots correspond to galaxies that are inside of the region of interest of this event. And this was made by the group of the SWOPE telescope, who has a small field of view telescope. These squares here are their field of view. And so their strategy was to target those galaxies in order of probability and try to find a counterpart that way. Our strategy was different. As I said, we have a wide field of view camera. So instead of pinpointing individual galaxies, what we did was scan the entire region and do it multiple times so that we could do a systematic blind search. This here is the 50% and 90% area, and the red hexagons correspond to the footprint of the camera in the sky. So those are our images. We did observations starting right after sunset in Chile, and we covered the entire area multiple times. We had a team of observers that were on site in Chile, also at Fermilab at the remote observing station there, and in several other places working from home, before working from home was a thing. And really many eyes, on the images, trying to pinpoint the location of the source. And all that effort did pay off big time. Here is a screenshot of the email that one of our collaborators circulated just circa 1 hour after we started doing the observations. And again, I'm showing the image that you saw on the first page, highlighting the location of the optical counterpart of GW170817 and its host galaxy, very bright galaxy, bright elliptical galaxy. Now, as I said, we were not the only ones looking. There were many other teams looking, including the SWOPE team that had a small telescope, and they saw it too. We were typing our answer, our report, when we saw their announcement that they had seen it as well. And I think that this is a good example of how sometimes an instrument with a modest size, a feature, can make a big impact in the field. This is their image, a little bit blurrier than ours, but you can see here clearly there is an object there, which is the counterpart of this event. In the future, I think it will be harder for 1-meter telescopes to make such an impact because the events will be further away and fainter. But this was an example where things worked out nicely. Other 4 groups, also independently from each other, discovered the optical counterpart of GW170817, and these are the papers where they report their discovery. We all gathered in Washington, D.C. later that year to make the announcement of the discovery to the world, and this was really one of the most exciting moments of my life as a physicist, and I think that this is something that I will always be proud of and would like to share. I think that this was really exciting moment. And one question that often comes after this is like, what now, right? We discovered one event. Can we do it again? Can we do it systematically so we build a sample of many events? Can we do cosmology, which is, in my case, my main motivation? So here is an example of trying to do a cosmological measurement with only one event. With 2017-08-17, what you're seeing here is the posterior distribution as a function of h naught, the same parameter that I showed before, the rate of expansion. And the vertical lines are the previous results from supernova and from the cosmic microwave background experiments. And as you can see, this measurement here is very broad. So we are not in position to say that either supernova or cosmic microwave background are the right answer here. But it is a measurement made with only one event. When we add more and more events, we expect our results to narrow down and then be, focused on the right answer. And I think it's really exciting that we can see already a trend in that direction with only one event. Now, we also, I mentioned earlier that before GW17 and WAIT17, there were several events that LIGO saw that we didn't see the counterpart, and they were all black hole mergers. Black holes, as far as we can tell so far, we searched, we didn't find a counterpart, so we have to assume that they are dark. There's no bright emission to do cosmology, so to observe. But it doesn't mean we cannot do cosmology with it. The idea here is that we have observations of galaxies in the area. So this is an example of a black hole merger that happened just a few days before the big event, the big neutron star event. And the colorful map here that is shown is a distribution of galaxies observed by DES. So you can see that there is a little clump that more or less aligns with the region where the event happened. So statistically, we can assign a probability to each galaxy to be the host, and we can use that to obtain a measurement of H naught as well. This likelihood analysis, we did that for this one event, GW17 weight 14, and compare with 08-17. What you see here, it is 14, and the narrow one is 17. So if our idea is to narrow down into the region of the purple regions here, clearly it looks like we're going the opposite direction, right? But the advantage here is that the black hole events are way more abundant in the LIGO data than the neutron star events. So for one event, you're not winning the game with a black hole merger, but over time, statistically, it is possible that we will collect more black hole events, enough events that we will surpass the statistical power of the neutron star mergers. So this was the state of the art for us around 2018, 2019. We did, at that point, we had, 2 observing campaigns. The second campaign, we had the big discovery of GW17 weight 17, and we had this idea of pursuing what we call the dark sirens, so gravitational wave events without electromagnetic counterparts. So what have we been up to since then? There was one more observing campaign, and that was the observing campaign 303 for short. During that campaign, there were many gravitational wave events, 3 of which are important, that I'm going to describe here. And these 3 events, they were well localized. One of them was a neutron star merger. The other one, we think, was a neutron star merger, but with low significance. One we think was a mixed neutron star black hole event, the first of its kind. And the other one was a black hole merger of small area. So we pursued, in particular, the ones for which we expect to have at least one neutron star. We observed the region of interest for these events a lot, and we did a complete analysis trying to find the electromagnetic counterpart, doing the same exercise that we did for GW17 and 17. In this case here, we did not find the optical counterpart. Otherwise, I would be showing a pretty image of them here. And the reason why we didn't find it is in part, we think, because these events are much further away, and because we think that the total amount of mass ejected is probably much smaller than the case of GW170817. Remember that I mentioned earlier that we expect that it's about 1% of a solar mass that is ejected. Here in this plot, I'm showing mass ejected, velocity of the ejected, circa 10% of the speed of light, and different values of the opacity of the material. And as you can see here, this here was GW170817, and right in the middle of the parameter space. And so the fact, if this event here would have been exactly the same as GW170817, we would have detected it with very high likelihood. But the fact that we didn't indicates that probably this event is unlike GW170817, it had less mass ejected or higher opacity. Okay. And same thing for the mixed and SBH event. We also think that this one was likely different from 2017 weight 17. And this is something that is interesting because we didn't know until this point how typical was 2017 weight 17 from the point of view of its astrophysical parameters. So what we did then, since we did not find counterparts for these events, we used them as if they were dark sirens, and combined the result here. What you see is again the posterior distribution versus H naught, and it's centralized. The combined result of all of these events is shown in red here. So we are making improvements with respect to the original measurement here, and we expect to improve much faster in the fourth observing campaign that will start in 2022. So this is where we are right now, and we are preparing for the upcoming observing campaign. Here are projections showing, based off what is the estimated increase in sensitivity of the LIGO detectors. If we are able to find counterparts for all of them, this is how quickly we would progress in reducing the uncertainty on the rate of expansion of the universe today. And the 2% line here represents the current uncertainties in this parameter that is achievable with supernova. So we expect that we'll be able to make progress in the time scale of less than a decade, make progress so that gravitational waves become a precision measurement tool for cosmology. And this is going to be extremely exciting. And this during this time when we hope to make progress in seeing more gravitational wave events being detected, we also have the expectation of seeing new instruments going on sky. So DES, that I showed the beautiful camera that we built in 2012 and so on. Well, DES will continue to operate for many years still. I mean, DECam, the camera that DES used, will continue to be operating for many years. But meanwhile, we have a new spectroscopic instrument that we can use in the in a program like this. And we also have the upcoming LSST camera that my team actually now I have students who are working on the commissioning of that camera, which will be one order of magnitude larger, which means we are likely going to have an easier time discovering the counterparts for events in the future. So this is all, I think, very exciting and bodes well for the future of cosmology with gravitational wave events. So in summary, I would like to end here so that we have plenty of time for questions. In summary, the DES gravitational wave program, DESGW, leads search and discovery program for the electromagnetic counterparts of gravitational wave events. We were fortunate to help inaugurate the era of multi-messenger astronomy with gravitational waves with the spectacular event GW170817. Thanks to the rapid discovery of the counterpart of that event, there were a number of studies that were made of the astrophysics of that event, follow-up observations, and so on, and also cosmology measurements, right? So we hope we'll be able to do this again for many more events in the upcoming observing campaign, using the lessons learned from the past 3 campaigns. It's been really exciting journey, and I'm really happy to have had the opportunity to share this with you today. Thank you.
Thank you, Marcelle, for the very exciting talk and very clear. Now we open for the questions. So we have Red Betty, please. You can take the first question.
Oi, Marcelle. Great talk. It's always nice. You are always very, very clear and bright. So, Marcel, I have 2 questions. One regards the tension with the cosmological parameters, the Hubble constant, all this. Do you believe? I mean, it's not believing, but what is the because with the number of events, as you showed in your last slide, you can improve the uncertainty, right, towards the measurements of the Hubble constant. And what is the error, not the error, but the direction of this improvement is in going into the direction of decreasing the tension or increasing the tension with the other measurements? This is the first question.
So I would prefer to have more data, to be able to say something definitive about what direction things are going. But given that we don't have more gravitational wave events yet to answer the question, I think we can borrow from other observables. So every time that we make measurements using observables that involve the modern universe, there seems to be a discrepancy with respect to what we get from measurements of the cosmic microwave background. So given that the gravitational wave events that we are observing are also in measurements in the late universe, I would be surprised if our measurements were more consistent with the CMB than with supernova. But we actually don't know. We don't have further measurements there.
Right. Okay. So the tension is still, this is open, right?
Yeah, I would expect that the question of the tension is still open, and I would expect that the results that we are going to obtain are likely going to help us explain what is the cause of the tension, but not make it go away.
Right. Okay. And the second question, okay, back into your master project when you studied the equation of state of dark matter, dark energy, Chaplin gas, all this stuff. Since then, have you had the chance to go back to these theoretical issues and explore? Have you gotten some new results on this? Did you have the chance to explore this theoretical side?
Mm-hmm.
You started the master here in IAG with us. Mm-hmm.
Yeah, so I haven't really explored much of the models, the constructing models and trying to come up with the predictions and so on. I am currently more at the other end of the process, trying to figure out better ways to make the observations that allow people to verify their models and improve them. But I'm not involved in making that, the theoretical end of the analysis at the moment is not being part of my focus.
Right, but anyways, it was,
very exciting time, and oftentimes I come back to think about that as something that I did not expect would have such a long-lasting impact in my own trajectory.
But anyways, you were doing on the observational side of cosmology. You were doing great. So, okay, Marcel, nice to see you, even remotely, and yeah, let's hope
Thank
that
you.
we can see you in person soon. Okay, thanks, Reinaldo, and thanks for the time.
Marcelle, I have one question myself. If you so if I understood, if we would have more gravitational waves detectors working maybe in the next decades, so would it improve? Would it narrow the area in the sky where you have to search? So it could speed up this prognosis you showed in the slide 31, this prospect for the near future. Is there
Definitely.
is there any good
Yes.
news in this sense that you know about detectors?
So yes, if you have more detectors, and in particular, depending on how you optimize their distribution on Earth, because the principle there, in order to get from the gravitational wave signal to a localization in the sky, is not unlike the way we use our ears to tell the difference between sound coming from one side of the room or the other side of the room, right? The difference in time of arrival plays a role, and also the differences in the amplitude that you perceive, right? So your brain does the processing very quickly, and you can turn your head and look and find the counterpart of whatever bright noise that you hear. Here, the logic is similar, and with more detectors, your ability to triangulate the signal is improved. That is for sure. In the near future, the good news in that front is that in Japan, the Kagura detector is being built. Currently, these forecasts that I showed, they don't include Kagura at all, okay? But if they are able to start operating in the next, few years within that timeline, at the level of sensitivity that they had originally planned, then of course they will contribute, and that means that we have the probability of having well-localized events. So this is something that we are very excited about, and that would make our lives easier from the point of view of trying to find the counterparts. It would be better if we had smaller regions in the sky, so we could spend more time in the same area and look for fainter objects, for example, right? And so on. So that is something that we are all very eager to see this detector coming online.
Great. So probably it's things will be even more optimistic than your the prognosis you showed. Probably.
I hope so. Yes.
Yeah. Thanks. Pedro. Pedro has a question, please.
Good afternoon, everyone. Good afternoon, Marcelle. Uh, I want to ask a question. If, like, gravitational waves measurements show a Hubble constant value close to the supernovae measurements, would it be sufficient to say or assume that the cosmic microwave background measurements has systematic errors or something like this? Or will it need more things to assume this kind of thing?
Thank you for this question. So if we are in a scenario where we have this new independent measurement agreeing more with the supernova measurements than with the cosmic microwave background measurements, what does this mean? Well, it doesn't mean that there are systematic uncertainties plaguing the microwave background measurements, right? On that area, we have a number of efforts being made also to mitigate those systematic uncertainties. What this would mean if we achieve that type of result, it is the only thing we can say in that scenario is that we think that systematic uncertainties are not the source of the discrepancy on the supernova side, right? On the cosmic microwave background side, it could still be that there is some source of systematic uncertainties unaccounted for. In the absence of systematic uncertainties, or if those systematic uncertainties are believed to be controlled, then we would say that that is evidence for some new physics, meaning that the typical lambda CDM model would be incomplete, and we would have to impose or to bring perhaps, for example, what Betty was mentioning earlier, bring in some more exotic model for the equation of state, of dark energy, or bring in some exotic model for the particles that are present in the early universe. So some people talk about sterile neutrinos or whatever, things that could affect the cosmic microwave background signal enough to make it compatible with the results of supernova, but are not necessarily systematic uncertainties. So all of that will be, I can anticipate already that regardless of what is the answer that we come up with from the gravitational wave point of view, we will have a lot of work to do going forward in order to disentangle what is going on and figure out what is the actual physics.
Thank you, Marcelle. Thank you so much.
I have a question. Maria, please.
Yes, thank you. Thank you, Marcel, for this great talk. I have a question regarding to you were saying you were searching to see how typical the event of 2017 was regarding others. So concerning the parameters of the system that is producing, I guess, the electromagnetic emission, you get to narrow it to two. Is that correct, what I understood, to the mass ejection and the opacity? Can you comment on this, please?
Definitely. So there are three key parameters in this model. And I should say that this model is very simplified in the sense that, for example, we consider the emission to be spherically symmetric and so on, right? So you can make it more complicated, but in the case that I showed here, it is a simple case with three parameters: the mass ejected, the velocity of expansion of the mass, and the opacity. So the opacity is an indirect handle on what fraction of lanthanides was produced, right? So I skipped this part, but the origin of this radiation is coming from nuclear reactions that are going all the way to the lanthanides in the periodic table, right? And so in detail, the rates of in each of those processes and so on, and what is the abundance of each of the elements that you produce will result in a different opacity, right? So so that is the other parameter that we consider. So big question was, okay, was GW17 or 817 particularly bright? But we don't know. We have only one example, right? But based on the searches that we made for these other two events, I don't know, it could be that it was particularly bright, which would be unfortunate because it
Yes.
means that the challenge will be much bigger.
Yeah. Okay. I understand. So actually, you would have through the opacity, you have sensitivity with the metallicity, actually.
Yeah, it's an indirect parameter. So there, also the other thing I should say is that the opacity would have two effects, right? It's reducing the overall brightness, but also it's making things redder. So that is also another consideration.
Yeah.
That would mean going more and more towards the infrared. And if it goes too much into the infrared, then it becomes difficult for us with the ground-based telescope.
Yeah, you will miss it.
Mm-hmm.
Okay, thank
But
you.
we still don't know, right? It's only a handful of events so far. Another thing that I didn't mention also is that from the gravitational wave data, the estimate of the ratio of the masses for the system that is mixed neutron star black hole. The estimate is that the ratio of the masses is big. And if that is the case, one possibility would be that in that particular merger, the merger occurred without disruption of the neutron star material. So if that would be the case, then obviously we wouldn't have any emission, right?
Yeah.
But we don't know.
Okay. I would like to thank Marcelle again for the seminar. Thank you a lot, Marcelle, for being here, sharing your research with us. I'd like also to thank everyone participating here in Google Meet and YouTube. And I think from now we will finish the broadcast to YouTube.
Oh. All right. Thank you, everyone. It was a pleasure.
Ok, agora